Lesson 107. In this lesson, we are going to look at the vector or cross product of two vectors. When we find the cross product of two vectors A and B, we use the notation A cross B. Okay, so this is a reserved operator for vectors. When we do that, the resultant of A cross B will be a perpendicular vector to both vectors A and B. So here I'm going to show you how we actually come up with the algorithm for calculating the vector product of two vectors by letting vector A, A1, A2, A3, vector B, B1, B2, B3, and vector C, which is like the simplified version of A cross B, by calling it X, Y, Z. We won't really carry out the whole derivation, but hopefully this will give you an appreciation for how we come about with the algorithm for calculating cross products. Since we know that the cross product of two vectors is perpendicular to the individual vectors, I can say that we know that vector A is perpendicular to vector C, which also implies that the dot product of A dot C is 0, right? So what does that mean? Using the components of these two vectors, I can write A1x plus A2y plus A3z equals to 0. This is one equation. I'm going to do the same thing with vector B. And this will give me the equation B1x plus B2y plus B3z equals to 0. This is a second equation. So what you do is you can solve this system of equation, okay, for x, y, z, and eventually you will arrive at the result, which gives you the actual algorithm of how you can calculate A cross B, which is as follows. The x component of this is A2B3 minus A3B2. The y component is A3B1 minus A1B3. The z component is A1B2 minus A2B1. So sounds pretty difficult to remember. So an easier way to look at this is that you'll list the components of vectors A and B across, and then you ignore the first column, and then what you'll do is that you're going to multiply downward A2 times B3, subtract going up A3B2, right? That's the x component. You repeat the process, A3B1 minus A1B3. One more time, A1B2 minus A2B1. Those of you who might have watched some YouTube videos or you have learned vectors, cross products before, you may have another method by using determinants. I may record a section at the end as a bonus. Okay, you can use that method too. But for now, this is a more foolproof way because you only have to think about, think in one direction and remember how to multiply and then subtract, multiply and then subtract, okay, and so on. So we say that any vectors that is perpendicular to two vectors, say vectors A and B that are non-collinear, then every vector perpendicular to them would be a scalar multiple of the cross product, K times A cross B, okay? So let's try to, work out some cross products. Here you're given vectors A and B. We are going to look for A cross B. So the first thing that I'll do is let me list out the two vectors sideways. Okay, and then what are we going to do? We're going to ignore the first, and then go down, and then go up like that. We follow that pattern, right? So x component, I have 1 times -1 minus 2 times 1. And then the y component, I have -4 minus -3, so plus 3. 3 times 1, 3, minus -2 times 1 plus 2. Simplifying this, I get -3, -1, and 5, being the cross product of A cross B. Part B, we're going to look for a unit vector that is perpendicular to A and B. Well, we know that this vector will be, in the same direction as the cross product. So that means we can tick the unit vector of A cross B to achieve this aim of A cross B. Okay. So I will need to calculate the magnitude of A cross B. So -3 squared, 9. 1 squared, 1. 5 squared, 25. Times -3, -1, and 5. So I have 1 over square root of 35 multiplied to every component. And that's the unit vector that we are looking for. Okay. Now to check whether, we have done this correctly, we can now find the dot product of A dot A cross B, because if the two vectors are actually perpendicular, I should get a 0 scalar vector, right? Let's see. So vector A is 3, 1, 2. A cross B is -3, -1, and 5. I have -9 minus 1 plus 10, which is 0. That's good. Let's do the same with vector B. What do I have for B? I have -2, 1, -1. Dot -3, -1, and 5. So here's 6 minus 1 minus 5. Indeed, this is also 0. All right, so next, let's take a look at some properties of cross product. We say that cross products are anti-commutative, meaning that A cross B compared to B cross A will have the same direction. Well, not the same direction, but opposite direction. Okay, you still produce perpendicular vectors to vectors A and vector B, but they will be pointing in opposite directions if you switch the order of the cross product. Scalar multiple can be applied to the entire cross product, or it can be applied to one single vector before you cross, and you will still get the same result. And distributive property will hold true in cross product. Okay. So example 2, prove the algebraic definition of the vector product to prove the scalar multiple property. So here we're going to prove K times A cross B is equal to K A cross B is also equal to A cross KB. Okay. So to help us with the work, I'm going to first let vector A to be A1, A2, A3, and vector B to be B1, B2, B3. Okay, so let's work out A cross B. A cross B is, if I ignore the top row, A2, B3 minus A3, B2. And then I'm going to have A3, B1 minus A1, B3. So you see the middle, like the current row is missing from that calculation. 2 is missing, right? So in the third row, we'll be seeing 1 and 2s. So A1, B2 minus A2, B1. Like that. So now this will allow me to say that K times A cross B is equal to KA2B3 minus KA3B2, KA3B1 minus KA1B3, and KA1B2 minus KA2B1. Okay, so this is our basis for the scalar multiple property. The next set that we're going to prove is KA cross B. Okay, so the vector KA is KA1, KA2, KA3. Crossing it with B1, B2, B3. Okay, so let's see. Here, we won't have any ones, right? So it's almost like, when you think about this, how can I do this? Ignore that, and you're crossing, like finding your algorithm like that, okay? So I'm gonna get rid of that. All right, so going back. So KA2, B3 minus KA3, B2. And then in the second row, right, ignore this. But then remember, we are kind of like stacking the numbers like that when we do the cross product. So in this case, I'm going to have KA3 B1 minus KA1 B2. Not B3, sorry. There won't be any 2's here. Okay, and the last one, you ignore the last row. You have KA1 B2 minus KA2 B1. Okay, which is so far the same as K times A cross B. Okay, so we have proven this first pair in the scalar multiple property to be the same. And then we'll do the same for this time A cross KB. Okay, so A is A1, A2, A3 cross KB1, KB2, KB3 this time. Okay, all right, so I have, ignore the first row, A2 times KB3. So that's K A2B3 minus A3 KB2. So K A3B2. Ignore the middle row, A3 times KB1, KA3B1 minus that way, and then KB3 A1, which is the same as KA1B3. And then ignore the last row. I have KB2 times A1. So KA1B2 minus A2 times KB1. So KA2B1. And of course, this is also the same as K times A cross B. Okay, so we have proven the scalar multiple property. Since cross product is a vector product, it has a direction, right? In order to determine geometrically the direction of a cross product, if I'm looking at U cross V, you will have to use the right hand rule. Okay, so what you'll do is you align your fingers. You open your palm, you align your fingers along the vector U, and then you curl your fingers towards vector V. And then the direction of your thumb gives you the direction of U cross V. Okay, so that's why this is what you see in the diagram. So now I want you to try this. What is the direction of V cross U? So you line up your fingers along V. This time you curl towards U. Okay, you must curl towards U using your right hand. Okay, naturally, which way is your thumb pointing towards? Your thumb should be pointing towards the down position. Okay, so that's, and clearly you can see why u cross v is the opposite, is negative of v cross u now using the right-hand rule. Okay. To calculate the magnitude of a cross product, you can multiply the magnitude of A times magnitude of B multiplied by sine theta. Okay. In physics, this is related to torque, turning, anything that has to do with turning. And note that theta is the angle between the two vectors A and B, and it is not greater than 180. Okay, we're only considering a straight line here. All right. So let's calculate in example 3. If magnitude of u is 6, magnitude of v is 8, the theta between them is 30 degrees, find the magnitude of u cross v. Very simple, because you're just multiplying or substituting values into the formula, okay? So 6 times 8 sine 30 degrees, and sine 30 is 1 over 2, okay? So this is 3 times 8, 24. And then here we have 4 vectors A, B, C, D. State whether the results are scalar, vector, or meaningless. Okay, so let's take a look at this. A, I have the magnitude of A cross B times C. Magnitude of A cross B, a vector, is scalar. And then C is a vector. So this gives us a scalar multiple of C, okay, which is meaningful. B, we have A cross B, a vector, vector cross C, a vector, and then vector dot vector D, dot product is scalar, okay? Next, I have A cross B, a vector, A dot B, a scalar. Can I add a vector and a scalar together? No, this is meaningless. D, what have we got here? I have A dot B cross C, so I have A dot a vector, okay, that's fine, dot D, all right. So A dot B, a dot product, gives me scalar. Scalar dot D. So this is different, right? The dot here means vector dot. So this is meaningless. Okay. So going to example 5. Given two collinear vectors A and B, find a nonlinear or non-zero vector perpendicular to A and B. So today we have seen that, well, if we have two vectors, the easiest way to find a perpendicular vector is to find a cross product. However, we have a problem here because these two vectors A and B, they are collinear, meaning B is actually, and if you look at it, B is actually equal to 2A, right? And because theta between them is equal to 0, what does that imply? It implies that A cross B has a magnitude of 0. Okay, in this case, cross product is not as useful. So what does that mean? Well, if we have perpendicular vectors, we can still talk about dot product. Okay, so we're going to let the vector that we're looking for, vector v, to be x, y, z. Okay, what I know then is A dot v must equal to 0. And what does that give me? 1x, 2y, 3z is equal to 0. Okay, and then b dot v is also 0. So I have 2x plus 4y plus 6z equal to 0. I know that, these two equations are actually identical. So what I can do is to use parameters to solve the system of equation. Okay, so we're going to let a to be x and b to be y. Then I can say that a plus 2b using the first equation plus 3z is equal to 0. So z must equal to negative a minus 2b over 3. Okay, this results in infinitely many solutions. Infinitely many solutions. For example, so feel free to pick any values for a and b, say 1 and 0, and then I have negative 1 minus 0 over 3. So negative 1 over 3 would be one of the many vectors that is perpendicular to a and b. Okay, if I pick 2 and 2, I have negative 2 minus 4, so negative 2 minus 4 over 3, or 2 to negative 6 over 3, so negative 2. Okay, that's another vector that will be perpendicular to a and b. All right. In the next section, we're going to look at some more interesting applications of dot and cross products related to finding areas and volumes of shapes. We're going to start by looking at the area of a parallelogram with side lengths u and v, or represented by the vectors u and v. We know that the area of a parallelogram is base times height. So we can use u as the base. So I know that part of this formula is going to involve magnitude of u. Now, how can I find the height using the given information theta and the vectors that I have? Well, notice how in the right triangle, I can say that height over magnitude of v is equal to sine theta, right? That's opposite over hypotenuse. In other words, height is equal to the magnitude of v times sine theta. What do we notice? The area of a parallelogram can actually be found by finding the magnitude of u cross v. Pretty convenient, right? So let me box this. And so we can extend this to see how we can find the area of a triangle. Well, area of a triangle is technically half of a parallelogram, right? So I can now say that the area of a triangle is 1/2 of a cross b in this diagram. Okay. So example 6, determine the area of a triangle with the vertices A, B, and C given. All right. We don't have to, put these points in 3D space, but what will be useful is that we can just sketch out a vector diagram. I have A to B, B to C, and maybe AC like that. Doesn't matter. So let me label A, B, C. Okay. What I need would be the magnitude of two vectors with a tail-to-tail connection. You can use BABC, you can use CACB, you can use ABAC. So for simplicity, I'm just going to do, I need that 1/2, AB cross AC. Okay. And recall how we can actually find these vectors using position vectors. AB is B minus A, OB minus OA. So I have 3 minus -2, 0 minus 1, -1 minus 3. Okay, cross. AC is OC minus OA, so 0 minus negative 2, 1 minus 1, negative 2 minus 3. All right. So what are we actually crossing? We're crossing 5, negative 1, negative 4 by 2, 0, negative 5. Okay. If you like the horizontal method, you list out 5, negative 1, negative 4, 5, negative 1, negative 4, 2, 0, negative 5, 2, 0, negative 5. Okay, so we ignore the first column. We go this way, that way, down, and then up. All right. Okay, so we need the magnitude of this vector. Negative 5 times negative 1. So 5 minus 0, so 5. And then next, negative 8 plus 25, 17. 0 minus negative 2, so 2. I need the magnitude of this vector, so 25 plus 289, I think, plus 4. Okay. And this works out to roughly 8.92 square units if I round it to 3 significant figures. Another useful application of cross product is to calculate the volume of a parallel pivot. Parallel pivot is basically, this shape that's formed by 3 vectors, and then you have opposite faces being parallelograms, okay? So because all the faces on the parallel pivot is a parallelogram, obviously, to calculate the volume of a 3D shape, we can multiply the area of a base by the height, okay? So the area of the base can be taken care of in this case by showing the magnitude of A cross B. All right. Now we need to find a way to calculate the height of this parallel pivot. Well, notice that the height is in green. And then if I assume that if I call this angle theta, by zigzag, by alternate angles, this is also theta. So theta is an angle between the height and vector C, meaning that if I say height over vector C, or the magnitude of C, what relationship do I have? I have adjacent over hypotenuse. This is cosine theta, okay? In other words, I can say that the height of a parallel pivot is magnitude of the third vector times cosine theta, all right? What does that look like? A cross B is a vector itself, right? So magnitude of a vector times magnitude of another vector, cosine theta, is a dot product. Okay. So as you can see, well, dot product could be negative, but I don't think so. But just to be safe, I think your book has the absolute value in it. All right, so this is actually an interesting relationship because it's the volume calculation that involves both cross product and dot product. And sometimes we call this the triple scalar product. And as you can see, because all the faces on parallel pivot, they are all parallelograms, right? So you don't have to go by A cross B dot C. You can actually do A dot C cross B or B dot A cross C. They're equivalent. Magnitude, okay? Like that. So here is example 7. Find the volume of a parallel pivot determined by these 3 vectors. So let's just go by the easiest version, which is A cross B dot C. Okay, so let's work out A cross B. All right, so what do we have? 5, -5, -0, -4, -2, -6. And then I have 2 times 0, and then minus 4 times 5, so 20. Okay, and then dot with vector c, 3, -1, -1. Okay, what do we have? I have -15 plus 6 minus 20. So I have -35 plus 6, -29. So 29 units cube, like that. Another special use of the triple scalar product is in the proof of whether vectors are coplanar or not. So if you think about the triple scalar product is used to find the volume of a parallelepiped, right? But if the 3 vectors that are used to form a parallelepiped are coplanar, what will happen to the volume of that thing? It will be 0 because you get a flat parallelepiped. Makes sense? So let's write down the assumption here. If U, V, W are on the same plane, or lie on the same plane, let's do that. I.e. coplanar, then U cross V dot W should equal to 0 to indicate a flat parallel pivot. Let's fit this in. Okay. All right. So let's work out U cross V first. We have, okay, let's list them out. 1, 5, -2, 1, 5, -2, 3i minus j, 0, 3, -1, 0. Okay. So 5 times 0 minus 2 times 1, -2. -6, -1 minus 15, 14. Okay? -1 minus 15, -16. So -2, -6, -6. Okay, good. And then we will use this to dot W. W is 5i 9j minus 4k. So -10 minus 54 and then plus 64. So minus 10 minus 64, 0. Okay, so indeed, therefore, these 3 vectors, U, V, W, are coplanar. Okay. So the last application that we're going to look at is on this diagram. We know that a triangular pyramid has a volume of 1/3 of the area of the base times height. Notice how the area of the base is a triangle. And previously we said that, well, this is 1/2 of AB cross AC, right? And then in terms of the height here, if vector AD makes an angle theta with the vertical axis using Z pattern, this is also theta. And so if I consider the upright triangle formed by the height, and let's call this point AP, and then AD, the 3 sides here, the height of the triangle is actually the magnitude of AD cosine theta. Okay, let's put this together. I have 1/3 times 1/2 magnitude of AB cross AC times AD cos theta. So once again, I notice I have magnitude of a vector times magnitude of a second vector cosine theta. Once again, we have a triple scalar product of AB cross AC, the 2 vectors that makes up the base of the pyramid, and then dotted with one of the slant side, AD. Okay, like that.